Thank you, Christoph, for the introduction. Good afternoon, everyone, and welcome to my presentation about grid-friendly and efficient power supply for electric arc furnaces. In times of energy transition, I would like to first have a look at the source side, so how the electricity is generated. With the energy transition going on, there are more and more volatile inverter-based resources. And these sources generate flicker and harmonics. This doesn't happen in a conventional power plant with traditional rotating generators. But the conventional power plants will be closed sooner or later, so we have less rotating machines, and the short circuit power of the power grid goes down. It lacks of inertia. So facing these challenges, on the source side, there will be more and more stringent regulations for the load side. For example, in Germany, we have a quite stringent regulation. And just last month, the German Steel Association, VDEH, released a position paper where they complained about the low limits for flicker and harmonics. We learned about a lot of trends already today, and there are specifically two trends that are important when we look at power supply for electric arc furnaces. So on the left-hand side, we see on the electricity generation point of view a strong increase of the share of renewable electricity generation. At the moment, the world average is about 35%, and it is expected to reach 85% by the year 2050. On the load side, we expect a strong increase of electric arc furnaces, especially the scrap EAFs as an essential tool for the circular steel economy. So while the green renewable electricity generation is good for the climate, but challenging for the power grid. Electric arc furnaces are one of the most challenging load that you can connect to an electrical power grid. So to overcome these obstacles, there is a request for a new era of power supply for electric arc furnaces. The conventional power supply for an EAF consists of a furnace breaker, sometimes of a reactor with on-load tap changer, and a furnace transformer with tap changer. The length of the arc is controlled by the movable electrode arms, and the voltage is adjusted by the tap changer of the furnace transformer. But scrap melting is too dynamic for these slow electromechanical actuators. There remain strong current fluctuations, unbalances, and loss of arc. And this is causing tremendous trouble for the power grid. That's why the antidote to that is a separate compensation system that will be connected, as usual, in parallel to the EAF. So with the furnaces getting bigger and bigger, and with the advancements of the power electronics, we can see an evolution of the power compensation equipment for EAFs. It started with static filters. Then in the 1980s, thyristor-based SVCs came up, and in the 2000s, the IGBT-based STATCOMs. But for the future, the conventional technologies won't meet the ever stringent regulations. That's why we think that along with the transition to the green steel production, there will be a transition to a direct power supply for electric arc furnaces. And the main tool of a direct power supply for electric arc furnaces is an electric converter connected in series to the EAF. The slow electromechanical actuators are now being replaced by a converter with a stepless and very fast current and voltage regulation. There's no more need to have the separate compensation system. So, what are the main benefits of a direct power supply? First of all, we get rid of equipment that usually is responsible for a lot of maintenance work. So no more furnace breaker, no more series reactor, and no separate compensation system. The new technology makes it possible to meet the most stringent grid regulations also for the future. Only symmetric real power will be drawn from the power grid at the lowest possible flicker and harmonics. In addition to that, the system can provide separate reactive power dynamically to other consumers. And on the process side, there are also big benefits along with the new technology. We have a higher productivity, less losses, less wear and tear of the equipment, and also a more stable process. More than 70% of modern EAFs are connected to a medium voltage bus with a voltage of about 30 to 36 kilovolt. And having a medium voltage solution brings us several advantages. First of all, the power quality can be controlled at the point of common coupling, allowing to meet the grid regulations and to compensate other consumers of the steel plant. Second advantage is the installation flexibility that goes along with the medium voltage solution. So you can install the converter at any location in between the medium voltage switchgear and the furnace transformer. It can be a couple of 100 meters away from the EAF, no need to integrate it in the EAF building. And last but not least, the high current connection between the furnace transformer and the furnace, where we have the highest losses, remains as short as possible. And the existing transformer, or the transformer of the future, can become simpler because it is getting less stressed because we have the converter in operation. When we compare in more detail between conventional operation and converter operation, I have here some slides showing current and voltage of a two-basket melting process, and on the left-hand side you see the currents over the time. The black line shows the target current. The blue curve, this is real measurement of the actual current of a real plant. And the red curve shows the simulated currents using a converter. And obviously, all overcurrent conditions can be avoided reliably. Also, the effect of the current dips is much less compared before. So in general, the target current can be arrived in a much better way. And this is leading to reduced losses, and it opens also the door to new process functions that can be implemented using such an advanced tool. So besides of reducing losses, the new technology also allows us to bring in more active power into the furnace, especially in the boring and meltdown phase. As we can see in the chart on the right-hand side, so here at the beginning, boring and meltdown phase, the red curve, again, this is the simulated curve, compared to the blue curve, is certainly above of it. And bringing more active power into the process means we have a shorter power on time. That means an increase of the productivity. So the KPIs of the new technology in regards of the operation are a reduction of the power on time. In general, we say 10%. Reduction of the electrode consumption, 5 to 10%, always depending on the furnace, on the project, and energy saving around 8%. And there's another benefit having a converter in place. The converter is able to have an output frequency that is different from the line frequency. So we can operate at lower frequencies This is reducing the losses in the high current system, while operating at higher frequencies is stabilizing the arc in the boring phase. So the converter decouples the grid side from the load side. As we see in the lower chart, these are the EAF currents. So while the EAF currents are still subject to strong process-related fluctuations, the grid-side currents are symmetric and sinusoidal. And when I go back now to the table showing the different compensation technologies, and when we add the next generation power supply, we can see that the new solution clearly outperforms the conventional solutions. And in addition to that, we have the benefits of increased productivity, energy savings, and less wear and tear of the equipment. And I want to close with a quotation from Bill Gates, who wrote in his book in 2021, "We need innovation, not just in renewable energy, but across the board to get to net zero emissions. We can't solve climate change with the tools we have now. We need breakthroughs." Thank you for your attention.
Thanks a lot, Julian, for the presentation. It's very interesting to see that, with the quotation that you mentioned already, like emissions. We have received some questions here from our audience. I think we have time only for one question. Maybe just choose which one you would like to answer.
Okay, basically, the active power feeder can also be used for a smelter without any issue. And the second questions, since it is a Primetals solution, it will be seamlessly integrated in the automation systems that we have on place, including also our digitalization packages and so on. There's also one focus that we put on it. We don't just sell a kind of power electronics product. No, it is completely integrated in our process know-how and technology. And I think this is also one of the benefits that we can give to our customers with this solution.
Super. Okay. Thanks again, Julian.